morning, students. In the previous class, we have discussed about graphical representation of different kinematics terms. Basically, we have discussed about position time graph. There, we discussed displacement time graph and velocity time graph. We discussed about the different types of characteristics. What type of graph we'll find in case of a uniformly in a body that is in uniform motion, for a body in rest position. All these things we have discussed, and today we're going to discuss another topic that is also related to graphical representation, but today we'll discuss about the kinematic equations. Those in class 9 you have found as the equation of motion, as you got the three equations of motion in class 9, and those were V is equal to U plus AT. These are the first equation. Second was S is equal to UT plus a half of AT squared. Next is equal to use twice of AS is equal to V square minus U square. These three equations you have found in class 9, and hopefully you also proved this equation. But in class 11 standard, we'll try to go for representations of all these three equations. That means graphical representations of kinematics equation. You can write down the topics of today. That is graphical representation of kinematics equations. Okay, graphical representation of kinematics equation. Those three equations we're going to represent graphically. That's it. So first of all, we'll write down the first equation. That is, one more thing you can write, that graphical representation of kinematic equation, but there is a condition. We'll represent all those three equations only for an uniformly accelerated body. You write down this particular topic, uniformly accelerated body. That means that body must be accelerating in uniform motion, or that body should be accelerating uniformly. Am I clear? So graphical representation of kinematics equation, that is for uniformly accelerated body. We'll consider a body that is in uniform acceleration. So you first write down the first equation, that is V is equal to U plus AT. V is equal to U plus AT. Number one equation, V is equal to U plus AT. This ones we're going to represent. We have already drawn the position time graph. So again, we'll consider a position time graph in this case, in order to prove this particular, represent this particular kinematic equation. Say this is the position time graph. Again, we are drawing. Understand? So suppose this is your time and this is your position. You can say this is time, this side, this time. So you can say ST there. I'll write simply ST, that is time, and this side it will go as position. Understand? So in this case, if I consider that this point supposed to be 0. Now what will be the first case? That what will be what type of graph we found in case of a body that was in uniform acceleration? We found a straight line. But if I draw this straight line, and if the line is passing through the origin, that means we will consider that initial velocity is 0. If you consider that initial velocity of that accelerated body is 0, then the graph will go from here. But this time we will not consider initial velocity is 0. we'll consider that this body has the body initial velocity of this body is not 0. That means if you consider somewhere from here, what do you mean by here? That means the body is not, the initial velocity of the body is not 0. Am I clear? So if I make from here, the graph will show like that. Do you remember that? This was the graphical representation of a body that was in uniform motion or uniform acceleration. So if we don't consider that initial velocity of the body is not 0, so body will be coming somewhere from here. That means, what do you mean that I am drawing from here? That means initial velocity is not considered 0. Is that clear? So suppose this is the point, suppose from A to B. This is, what does it making? It is determining that this body has in uniform acceleration, but it is not from 0. Now I have joined this line. I have joined this line. And from 0 to O, this is your initial velocity. As you have known, this will be your initial velocity. And this is, suppose this velocity has start from here and it has ended up here. Understand? The velocity has started from here, not from 0. It has started from a certain point. It has started from here and it has got ended at this particular point B. So in order to find out the final velocity point, I have joined this line and say this is going to be your final velocity V. Now how much time it has taken to complete his velocity? To measure the time, I will have this particular line. So this is, suppose this is what this is. This will gonna be. This is also going to be indicated at what time this velocity has been changed to point B. So I have joined this line, and again I can join this line. I am joining this line. Okay. So this is, suppose A, this is B, suppose this point is C, this point is D, and this point I have taken as E. Understand now how I have drawn the diagram? I have taken a body that is in uniform acceleration, but its initial velocity we have not considered 0 this time. That's why I have taken the velocity, initial velocity from here. And suppose it is the final velocity has been ended at B point, and I have joined this E so that I can measure the final velocity. And I have joined this line, and so that I can get the time. And at what time the body has gained its final velocity. So in this case, I can do one thing. From this diagram, I can sum assumption from here. That means, as you can see here, that in this case this OA and BC are similar. That means you can write from the above diagram, you can write it is OE. This is OE is equal to OE is equal to BC, and OE is equal to BC. What is OE now? OE is the final velocity. So you can write OE is equal to BC is equal to final velocity. Have you got this point? OE is equal to BC, and what is OE? OE is the final velocity. So if OE is V, so BC is also going to be V. Next, this is OA. This is OA. OA is going to be your initial velocity. So I can write that OA is equal to CD. OA is equal to CD. They are equal. That means if OA is U, so CD is also going to be U. So OA is equal to CD is equal to U. That is initial velocity. Is that clear? Again, what we can write that this AD, you can see AD and OC are similar. So OC is T. So AD will also be T. That means I can write here OC is equal to AD, and this is going to be your time. OC is going to be equal to AD, so this is going to be your T time. So I have this assumption so that it's become easier for us to derive this particular equation. Now let us go for these things. Now very fast things. In order to derive this equation, we'll start from the final velocity. Then it will be very easier for us to derive the equation. So if I start from the final velocity, as you can see that final velocity is at 2, that is OE and BC is indicating the final velocity. If I consider this BC, so what does BC means? You can write now. Now BC is equal to this BC is equal to, I can write BC is equal to BD plus CD, I can write, or not. I can write BD plus CD. BC is equal to BD plus CD, I can write. Have you got this? BC is equal to BD plus CD, I can write. This implies, now what is BC was? Can you see here, this is BC. BC was your P, that is final velocity. So I can put the value of P here instead of BC. So BD, this is BD, this BD has no information. What is this BD? So I'm leaving this BD here. Plus CD. So this CD was your U, that is your initial velocity. Have you got it? So once I have started from this line, BC and OE are similar, and OE and BC both are indicating the final velocity in this particular diagram. So BC is equal to, I can write that BD plus CD as I have written here, and as per assumption I have put the value that BC has been replaced by phi, BD is similar, no information, CD is, this CD is going to be your U, that is your initial velocity. So if I write this is this number 1 equation, okay, if I consider this is this number 1 equation, or I can do one more thing, that if I do like that, so this implies BD is equal to phi minus U. This is number 1 equation. BD is equal to phi minus U. This is number 1 equation. Next, now we have no information about this BD, but we have to consider the we have to find the value of BD in order to derive this particular equation. Now what we do? Now what we know that we know that one thing, we know that what is acceleration? We know that acceleration is equal to, acceleration has got a formula that is change in velocity, change in velocity upon time. Change in velocity upon time, this is the formula of acceleration. Now in this diagram we can say which is the change in velocity. Change in velocity is nothing, this is from where, which point velocity has been changed. Velocity has changed, that means this is BC, BC is your what? Initial velocity. BC is your initial velocity, BC is your final velocity, and CD is your initial velocity. So change in velocity means, can I write that acceleration A is equal to change in velocity, final velocity minus initial velocity. So in this case BC is your final velocity minus BC is final velocity. What is initial velocity? CD. BC minus CD by time is itself t. So in this case I can write that acceleration A is equal to BC minus BD. If I subtract CD from BC, what will gain will BD. So I can write here BD by T. Understand? No? That means BC minus CD is equal to BC minus CD is equal to BD. This is equal to T. This implies I can write BD is equal to 80. The value of BD I have already got now. This is 80. Now if I put this value at number 1, from number 1 equation. What is number 1 equation was? BD is equal to V minus U. This is number 1 equation. What the value I have got for BD? 80. So it will be like that. 80 is equal to V minus U. If I add this equation, therefore V is equal to U plus 80, and this is the first kinematic equation, and that has been hence proof. V is equal to U plus AT, and this is what we need to prove. Understand? I hope you have understood. This is the graphical representations of first equation of kinematics, that is V is equal to U plus AT. I think you have no confusion over it. Diagram is very clear. You should understand. This is how we have represent the time. Okay, so all these things will be as usual normally what we have done. In the next class we will represent the next two equation. For today, that's it. Thank you.